So once again, welcome to iTelescope. My name is Christian Soss. I'm the astronomer in charge for iTelescope, and I'm very pleased today to introduce you to a PhD student, second year from UCLA, Sahil Hegde, and he's doing theoretical astrophysics. Sahil, welcome to iTelescope. There you are.
Yeah, thank you. Thank you for having me.
Very, very nice to have you. You know, your timing is impeccable. It's as if we planned this, because last week we had a brilliant talk. It was so exciting from Win, and it was all about stars, supergiants, and so on. And some people were starting, what about the population 3 stars? And wow, here we are. So anyway, Sahil, it's all over to you. So go ahead, please.
Yeah, I had a little bit of foresight about what I was going to talk about. All right, well, yeah, I'll just go ahead and share straight away. Okay, is that coming across okay?
It is. Go ahead, please. Yes.
Okay, perfect. So yeah, as Christian said, I'm going to be talking about the first stars in the universe, so the so-called population 3 stars, and I'll get into what that means, why we think they're interesting. Maybe you have a little bit of an idea already, but for me, I think it's always best if I, start with the basics and just, make sure that we're all on the same page. So let's start with a quick poll just to get us all warmed up. So what is a star? I'll read out the 4 options that I'm going to give you, and then Christian can launch the poll for everyone. So a conventional figure with 5 or more points that represents a star, something like this. Or, since I'm from Los Angeles, someone who might have their name on the Hollywood Walk of Fame. I certainly think that he's a star. A symbol used as a mark in printed or written text, something like that. Or a self-luminous gaseous spheroidal celestial body, yada, yada, yada. So
yada, yada, yada. I like that. Okay, here we go. Okay, you're going to get, this is really funny. Okay.
I don't think it'll take too long, so you can close it after.
Yeah, we'll do that. We'll just give people a few more seconds.
Yeah.
Then we still have a few. Yeah, there are more coming in. So just give them a sec, because there are also people coming in right now. Okay, so
yeah.
So we'll just be a little bit more patient, and then we'll go. Just hang on. We're still getting, give them a minute. Okay, we got 40 seconds so far.
Yeah. That's a tough question. So
it's a tough question. I love your sense of humor. It's great. Okay, let's see. Well, we nearly got it. Yeah, you got. That's going to be interesting. Let's see. Let's hear what you have to say. So I'm going to share the results. There you go. Any comments?
Wow. Okay. Yeah, we got some fans of The Rock here. There are 2 people. I like that. And then looks like a lot of us are tapped into, this thing down here at the bottom looks like a star. So yeah, let's jump in with that and let's keep going. So yeah, so that, in fact, answer D was, all of those are stars. All of the answers are correct, so nobody was wrong. But for today, we're going to focus on just one type of stars, and that's stars like our sun. So stars that look like this, if we were to look at them up close. And we're going to talk a lot about, what are stars, how they evolve, how do we observe them, both nearby and far away. So some of this might be review, but I think it's good so that we're all on the same page and understanding, what we're talking about. So yeah, just to start off, the simplest, closest, most familiar star for all of us is the sun. So the sun is our star. We are orbiting around the sun, and this is, as I said, or as that answer choice said, so as you told me, a gaseous celestial body that's, super luminous. It's powered by the fusion of hydrogen into helium in the core, and then those the energy that's released there gets, propagated all the way out to the surface and is then radiated towards us. And so we see this super bright object. If we looked outside, we would just see it as kind of a dot. But if we look up close and we, take pictures of the sun with telescopes, we can see that there is, really fascinating physics at play within the star and on the surface. And so you have these really complicated structures that are produced by the solar magnetic fields and things like that. And so you can get these really beautiful images. So with that, I think it's good to, preface and talk about, what do we know about stars in general? So you may have heard a little bit about this last week, but let's go through the life cycle of a star. So we'll go through each of these stages in detail, but in general, stars follow different evolutionary tracks based on how big they are when they form. So stars that are like our sun, so, a little bit smaller, maybe a little bit bigger, those will follow this track here on the left. Stars that are bigger than our sun, so, a couple times to 10 or 30 times the mass of the sun, or as big as the sun, will follow this track on the right. And they're similar tracks, but there are some differences based on, just how big they are. And so yeah, we'll go through each of these in detail now. So all of these stars will start in what are called giant molecular clouds. And I had to have this slide because there are some really beautiful images that you can get from these molecular clouds of, which is, really the birthplace or the nurseries from which stars are born. And so these are super giant clouds, hundreds of thousands of times the mass of our sun, that are, full of gas and dust. And from that, stars are born. And you might be asking, here you've shown me this thing that you're calling a molecular cloud, but I see nothing inside it. It's just a dark spot. And that is because, so all of these around here are stars and maybe some super bright galaxies that are in the background, but this dark spot is the molecular cloud. And that is a testament to how dense and how, massive this object is. So it's so dark, it's so densely packed with dust and gas that light from the stars in the back can actually pass through and get to our telescope. So we just see it as, rather than a source of light in the sky, an absence of light. So you can see that this is kind of like characteristic of what we would think of for a molecular cloud. It's a super compact, really collection of gas and dust. And then if you go to here, you can see that again, we have that kind of characteristic dark shape where there's these dust lanes that the light can't pass through. And you can actually see that a star has formed here inside this molecular cloud, and you can see that it's illuminating some of the dust around it. So it's blowing some of the dust away, and it creates this really cool, beautiful picture. And then at a later stage in a molecular cloud's evolution, you might get something like this nebula here. And this is a very famous picture, the Pillars of Creation. You may remember the picture that the Hubble Space Telescope produced, but then there's also, more recently, the James Webb Space Telescope, which has been releasing a lot of fascinating science in the last year, took a picture of these Pillars of Creation and allowed us to look into this stellar nursery. And you can see that this really cool looking structure is formed because of stars that have formed and released radiation that gave us these, very cool, like complex shapes because of the interaction of the photons with the gas and the dust. So we can see these molecular clouds and nebulae. This is part of the Eagle Nebula. You can see these in different stages of their evolution. So now that we've looked at the pretty pictures, we can talk a little bit more about the science. So here's my very rough attempt at putting together a cartoon for what is actually happening within these clouds. And we can, in detail, you have to run very complicated calculations. You have to run these simulations that solve all of these equations to figure out how exactly these clouds go from these, they're super dense, but how they go from these huge objects down to the density and the scale of an individual star. But intuitively, we can think about it actually very simply. So there are two forces at play when you have a big cloud of gas. You have the gravitational force, because this cloud is all gravitationally interacting. So the cloud wants to collapse. It wants to come together under gravity. But then you also have the fact that it is a collection of gas particles. So there's all these little particles of gas that I've shown here in the blue that are flying around in all different directions and bumping into each other. And that creates a pressure force, which basically pushes out against the gravity. So the balance between these two and the competition between them is what will support an object. So if you have an equilibrium between pressure and gravity, then the cloud would never collapse. You would never actually get to something that is so hot and so dense that you're able to perform fusion. And as we'll come to see, that's the key for something being a star. And so then you might ask, okay, how do we get gravitational contraction if the pressure force can counteract that? And so that's where the fact that these are molecular clouds comes into play. So if you see, I've zoomed in here on some of these molecules that are flying around, and I've identified that these molecules might be something like carbon monoxide. So while that is, toxic to us, if there was a whole bunch of carbon monoxide around, that wouldn't be so great. But for these stars, this is actually crucial to them being born. So the carbon monoxide and other similar molecules in these clouds, like there's, H2O, there are other molecules that actually, they absorb some of the photons that are flying around. They absorb some of the energy from interactions with other particles, and then they vibrate and radiate away some of that energy. And so these molecules are actually very efficient at absorbing the energy from individual collisions and radiating it away. So this is a really ugly photon that's coming out of that carbon monoxide molecule. And you can see that the vibration slows a little bit. It settles into a lower energy state because it's radiated away some of that energy. And what that does is it makes the molecule move a little bit more slowly. It has less energy to move around and bounce into other things. So what that does then is, if you remember, the pressure force is a result of these molecules moving around and bumping into each other. So if they're moving around more slowly, they're bumping into each other less, then the pressure force will be weaker. So through these molecular transitions is what it's called, these molecules basically make the cloud lose energy, and we end up with gravity winning and driving this collapse. So if we, summarize this, we can think about it schematically. So we have this cloud of gas, there are some clumps within it, and then each of these clumps is going to collapse into this pre-stellar core. And that's what happens as this cloud is radiating away energy. The gravity starts to win and it collapses down into this dense cloud of gas. And then as this cloud collapses, it starts to rotate and spins faster and faster, and it settles down into a disk. And then you get this thing that looks like a protostar. So it's something that's very close to being a star, but it's still too big. It hasn't, condensed to the high densities that we expect. And so then this continues to evolve. We get something which is a pre-stellar evolution stage called a T-Tauri star. And this process has taken, as you can see here, roughly 1 million years or so. And then finally, we get something that looks closer to a star. And so this takes, several million years to happen, but on the scale of the star's lifetime, as you'll see, that is actually very fast. So this gives us stars. And so we can look at this in more detail with this simulation here. And so this is basically showing you this giant molecular cloud that you have here. And you can see time going by up here on the top. And so this is, this is hundreds of thousands of years that are passing by very quickly. And you can see that the cloud is collapsing down to higher and higher densities. So the yellow-white areas are high density, and the red to black are low density. And you can see these clumps where the gas is condensing together to really high densities and forming stars. And now when we zoom into that, you see that as we continue to run the simulation here, that individual stars will start to form. And then as multiple stars form in the same place, they gravitationally interact, and some of the lower mass stars will actually get thrown out of their birthplaces. And so this is a complicated dance, and it leads to some very cool movies. But yeah, so this is kind of how you would solve that in detail. But once this happens, once you get the collapse and you get the condensation down to the high density of a star, then we get to, explain again. Then we get to what's called the main sequence life of a star. And so I'll explain what that means in a couple of slides, but this is basically what a star does for most of its life. For 90% of its life, it's going to be what we call a main sequence star. And that's basically defined by the fact that it's doing hydrogen fusion in its core. So it's smashing together hydrogen atoms to form helium. And in doing so, it releases energy, like I was saying, and that's what we see as these luminous objects like our sun. So that release of energy does the same thing as what we were seeing in the cloud before. It creates this pressure force, and that pressure force balances the push of gravity. And in stars, while they're on the main sequence, this is actually an equilibrium process. So they're roughly stable. And this is actually a very boring stage because they don't do very interesting things for most of their life. So then once you finish that main sequence stage, which for a star like our sun would be like 10 billion years of time, so it's a pretty long time, you get to the post-main sequence life. And so this is, I'm sure, what you heard about in detail last week. So I don't want to belabor the point too much, but the idea is you can see this is what stars like our sun would look like at various stages of their evolution. You start with the protostar here on the left, and then as time goes by, so our sun is, you know, middle-aged. It's only at 5 billion years old. So then by 10 billion years, the sun starts to leave the main sequence. It starts to inflate, and you get this sort of red giant phase, which you would see here. And so I don't think this is exactly to scale, but it gives you the sense of how the sun is going to evolve into this huge object. And for a star like our sun, the ultimate phase beyond that is it's going to go into a planetary nebula. So it's going to blow off these layers of dust and gas, and you get these really beautiful structures. So here's another picture from JWST of the Southern Ring Nebula, which is one such structure where you have all this dust and gas that's been blown off and a white dwarf here in the center. And then there's another nebula, which you can see from the Northern Hemisphere, which is just called the Ring Nebula. And here's a picture that I took with the telescope at Mount Hamilton in the Bay Area, California. But, you know, this picture, it's nice, but there are nicer pictures that we have of the same thing. So here's a picture that I did not take, unfortunately, but with the Hubble Space Telescope of the Ring Nebula. And you can see that it's a really beautiful structure. And with a telescope like JWST, which looks not in the optical, so this is an image in visible optical light. If you look in the infrared, you can actually look through some of this dust. And that's how you're able to see the star in some of these pictures, whereas in this one, you can't really see the star in the center. So for a star, this is what happens for a star like our sun. But if we're talking about a star that's more massive than our sun, then we get what you were probably talking about last week, which are supernovae. So here's a simulation of what's happening in a supernova. And this looks kind of crazy and weird. And I don't know too much about the physics of supernovae. I don't really work on that, but you can see that this is a process that's happening, if you look up here at the top, over scales that are much, much shorter than a second. And so there's this really complex explosion, basically, that's happening at the end of a star's life when it becomes the core of the star the outer layers of the star become too massive for the core to support them. And so then the core starts to collapse, and it collapses down to the super high densities. And when it gets there, then the outer layers start to fall down onto the core of the star. And as they fall in, they reach the super high density core, and they bounce off. And what this creates is this huge explosion, which happens over, the time scale of a couple seconds, and would be this, spectacular thing to see from very far away. You wouldn't want to be very close, but yeah. So that's like a simulation of what the individual fluid dynamics might look like. For a slightly more, artistic interpretation of what a supernova might be like, you can see this star is starting to, break apart and explode, and then you get this shock wave that comes off in a couple seconds, and then this huge explosion. And I don't think this is exactly what it would look like. If you were this close, you would probably not be seeing anything, but it is a spectacular thing. And we have observed these supernovae from very far away within our galaxy and in other galaxies. And so that's what happens for a massive star at the end of its life. And we'll talk more about that a little bit later. So then, having talked about, how stars evolve, how they grow, I think we understand, what we know about stars. This is a very schematic picture of what we know about stars that we observe around us in the local universe. So then you might ask, how do we know this? How do we observe these stars? And so here's the basics of observing just a star out in the universe. So what we do is we look at their spectra. So this means that if we look at the stars, we see light coming from them. And this light is emitted at a whole range of wavelengths. So there's red light, there's blue light, there's light that we can't see. So there's light in the infrared, and there's light in the ultraviolet. And we know about ultraviolet light because that's bad for us. Like we want to wear sunscreen to protect that, but we don't actually see that light as much. And so there's light across the whole electromagnetic spectrum. And so what we can do as astronomers is go out and take a spectrum. So we can look at the light from the stars, split it up as a function of its wavelength, and we can understand the temperature of the star and the composition of its interior, so the elements that make up the star, by looking at that spectrum. So we can look at the what are these called absorption lines in the spectrum. And these are produced because of these elements in the star's atmosphere. So if you have an element here in the atmosphere, it might absorb some of the photons that are coming to you from inside the star. And if it does that, then it'll hold on to that energy. And then we won't see a photon at that specific wavelength. So, by doing so, like if we observe a whole spectrum and we see a series of absorption lines, that tells us, oh, this star has this amount of these photons in its atmosphere. And so what this looks like in practice is this. So if the star had no elements in its atmosphere, we would see just this very smooth curve here on the left. But then because it does, we see this very jagged curve with these characteristic absorption lines. And this is very low resolution, but you can see that there are a whole bunch of elements that we identify in a star's atmosphere. And so what that does with the temperature and the composition, that tells us where we can put the star on this so-called Hertzsprung-Russell or HR diagram. So that's on this axis, we have the temperature of the star. On this axis, we have the luminosity or how bright it is. And so we can, calculate that for every star and we can plot it here. And this gives us, it turns out to give us this main sequence that we had just talked about, which is where the star spends most of their life. So based on how massive or how big the star is, it'll fall somewhere on this main sequence when it first forms, and then it'll live there for most of its life. And then as it evolves past the fusion of hydrogen, once it exhausts all of its hydrogen fuel, then it starts to leave the main sequence because the star's brightness and temperature start to change. And that's how you get these giant and supergiant stars that you were talking about last week. And then once some of these stars end their lives, they actually move all the way down here to this low luminosity, so not very bright objects called white dwarfs, but these tend to be super hot because they're super condensed. So this is just a schematic of how a star or a cloud of gas that we were talking about before, it'll radiate away its energy and then it'll become a protostar, and then it follows this characteristic track on this plot, which astronomers identify, and then until it finds its way to the main sequence. And then it just kind of hangs out there for several billion years. So that's what I mean when I say the stars aren't super interesting during that period of time, because they don't really do much on this HR diagram. So that's what a single star would do as it evolves onto the HR diagram and we find it as a point there. But if we looked at a collection of stars, a population of stars, this is how they might look. So we might see if all of these stars were the same age, but a whole bunch of different sizes, we would see this population of stars that all fall on the main sequence when they first form. So this is at time equals 0. Then as time goes by, so this is like 10 million years, this is like 100 million years, and over here is like 1 billion years. As time goes by, the more massive stars will burn through their hydrogen fuel more quickly because they're bigger and they're gravitationally contracting more, there's more mass, and they're burning more quickly, they're brighter as well. Then you see this, these stars start to leave the main sequence. And so you can see that that's what these arrows are showing you, is that you get this turn off of the main sequence where these stars evolve away and form that characteristic structure where you saw there were some stars that at the giant end and then some stars still on the main sequence. So this is what it would look like if you had a single population and you observed it at different times. So as stars of different masses evolve, they populate different portions of the diagram. But if we looked at something like our Milky Way, this is actually a collection of several populations of stars. So that means that you have stars that are on the main sequence, but then you also have some stars that have evolved away. You have some stars that have become white dwarfs. So you get this very complicated diagram that shows you all of the, basically the distribution of your population of stars. So that's what here is, like 22,000 stars that have been observed in the Milky Way and plotted on this diagram. And you can see that there are some stars that are lower mass over here that are probably going to stay on the main sequence for more than 10 billion years. So they'll be over here for a very long time. And then there are stars here, which, in a few 100 million years, they'll evolve off of the main sequence. And that's relatively quick on a stellar timescale. So all of this is, just generally what we know about stars. And maybe you know all of this. So this is review for you. So why don't we talk about the first stars? So here's our second poll question. So Christian can launch that now.
Okay, I did.
All right, so this one is just a simple yes or no. this one does have a wrong answer, but that's okay. So yeah, so why don't you tell me, what do you think? Are things different for the first stars?
Maybe we'll give it a few more seconds and then.
Sure, yeah.
Because now you're starting to get serious.
Yeah.
Okay, last 10 seconds. Okay, here you go.
See what we think. Oh, okay. We're pretty evenly divided. Yeah. A lot of people who think that there's something different, and some people think that I'm just playing around.
Here you go.
Well, I mean, I think one thing that's a giveaway. So the answer is A. Yes, things are different for the first stars. And you know, we got 20 more minutes, so we've got some interesting things to talk about. So yeah, so let's jump into it. Let's see why are things different for the first stars. So this goes to what is different in the early universe. So to understand why the first stars are different from that picture of star formation and evolution that I just described, we have to think about what's happening in the very early universe. And so, as usual, we start with the Big Bang. So at the Big Bang, the universe grew out of a single point in space. So there was this huge explosion, basically, and over a fraction of a second. So you can see here, this is 10 to the minus 32 seconds. So a teeny small fraction of a second, the universe grew and started to expand out of that single point. And then we had this period of cosmic inflation where, you know, things, as pieces of space that were the size of your computer screen grew to be the size of our solar system or a galaxy. So it was this super fast expansion of space that spread everything out super far over a fraction of a second. This is from 10 to the minus 32 to, like, I think 10 to the minus 32 seconds. Like, it was such a small amount of time. And the universe expanded out to be like closer to the size that we see it today. And then it continued to expand over time. But as a result of inflation, that period of expansion, we get these little fluctuations in space that give rise to, you know, this structure that we see in the universe later today, like later in its evolution. And so there's a lot of very interesting physics that goes on in here. But the main idea that comes out of this is that as the universe grows and cools down and expands, you actually are able to form these elementary particles, the things that make up protons, neutrons, electrons, that end up forming the elements that we see today. And so the end result of all of this, at basically 20 minutes after the Big Bang, so not even a half hour and barely, you know, shorter than the amount of time that I've been talking, we end up with the end of nuclear fusion in the universe. The universe has expanded and cooled down to the point where you have, you know, a collection of protons and electrons that are flying around in this big soup of particles in the early universe. And then as the universe continues to expand and cool down, slowly the particles start moving slower and slower. So they're not going to be colliding with each other as much because the universe, they're getting further and further apart as the universe expands. And by a period roughly, you know, 400,000 years after the Big Bang, we get this thing that you may have heard of called the cosmic microwave background. And I'm not going to talk about that too much, but the reason that I'm pointing it out is because this is the point where protons and electrons will combine and they will form neutral hydrogen. And because the universe has expanded sufficiently by this point in time, they're no longer moving fast enough that they break apart. So throughout all of this time between 20 minutes and 400,000 years, they were combining and forming hydrogen, but then it was so hot that they continued to bump into each other and break right back apart. Once we get to this point, then they combine, and then they no longer are able to find another hydrogen atom to collide with each other and break apart. And so we end up with neutral hydrogen that doesn't get broken apart. And so that seeds basically everything that we see around us. So we have this huge amount of neutral hydrogen all across the universe, a little bit of helium, but just hydrogen and helium. We don't really see anything heavier, no heavier elements in the early universe. And that's the key for why the early universe is different from the universe that we see today. So inflation gave us those little fluctuations that grow into these structures, as we call them, like stars and galaxies and things like that we see today. And then the process of fusion in the early universe gives us the neutral hydrogen that forms these structures. And so, so the idea here is actually that the first stars are actually pretty simple. We just have a whole bunch of hydrogen around. So the physics is actually not as complicated as what we were talking about before. So we don't have things like carbon monoxide. We don't have things that make the physics more complicated. We just have hydrogen floating around. And when you have only one thing, it makes the physics much easier to deal with, we think. So this is the key to any discussion of the first stars, is that this is a period of time in the universe that is very, very far away, or very, very long ago. So we actually have no observations of this time. So that means that all that we know about these stars is just based on theories. So we have lots and lots of models. People have run lots of simulations that try to explain how those first stars formed and what we think happened in the early universe. But all we can really see is that cosmic microwave background that I was pointing out earlier, but we haven't actually seen the stars. So we've seen things after the stars. We've seen some things before the stars, but we haven't seen things in between. And I'll explain why that is in a little bit. But because things are pretty simple, it's actually pretty quick to just talk about what we think that these stars were like. So this goes back to the point that I was saying before, which is that if we think about the composition of these stars, so what elements make up their interiors, they have lots of hydrogen and then some amount of helium. And then there are trace amounts of lithium, but we don't need to worry about that. That's just a feature from the Big Bang. If we compare that to the sun, which is shown over here, you see that it still has lots of hydrogen and helium, but there's this 2% of heavier elements, so like oxygen, carbon, iron. And that 2%, while it seems small, is actually the key to why the sun is a very different star than what we think the early universe stars were like. And so the reason for that, we can return back to my very crude drawing from before. So this is almost the same drawing, except the one key difference is that here I've replaced the carbon monoxide, or the C and the O, with two hydrogens, or what we call molecular hydrogen. So two hydrogen atoms that combine to form a molecule, or H2. So the reason that this is different is you have exactly the same picture of pressure and gravity, and you need to gravitationally collapse, except now you only have hydrogen that's doing the cooling, or that's driving out the energy and allowing the pressure force to become weak and the gravity to win. And it turns out that hydrogen is much, much worse at doing this than carbon monoxide or any kind of heavier molecule. And so you have exactly the same thing where the hydrogen is vibrating and it radiates away some of that energy, but it does so just worse than these other molecules. And that means that the cloud of gas can't collapse as far as it did before. And when that happens, it still forms a star, but it forms a star without, collapsing to a super small stage and breaking up into little pieces like we saw before. And instead you get one really big cloud, or one really big object that becomes a star. So what that means in practice is that you get one star that is basically like 100 or 500 times the mass of our sun. So you get this super huge, super luminous star from this process. And it ends up being very simple to think about how these stars evolve because they just have hydrogen in them. They evolve very quickly, and they're so massive that they burn through their fuel super quickly, and they live for only a couple million years, which, if you think about our sun is going to live for 10 billion years, that's a factor of like more than 10,000 shorter than our sun's lifetime. So these stars are super big, but then they also run through their fuel super quickly, so they live very short lives, and they might be gone before we're ever able to see them. And so we're going to talk about that as well. So then we can think about, what do these stars do for that short amount of time while they're around? And this is the key for how we think we might be able to study these stars. And this is that these stars, just like any other stars, radiate light. And as they radiate this light, some of this light is going to be in the ultraviolet. And these stars are surrounded by hydrogen everywhere. Like I was saying, it's just the universe is very simple. There's just lots and lots of hydrogen everywhere. And now you have a couple of stars that appear. And what they do is they radiate this light. The light interacts with the electrons that are in the hydrogen. So you have a proton and an electron, and they knock the electrons out of the hydrogen. And this creates basically a similar idea to these structures, where we saw that the dust and the gas kind of got blown away by interactions with radiation from the stars, and you get these kind of complicated structures in this case, in a molecular cloud. And it's an analogous to what we see in the early universe, where these stars interact with the hydrogen gas around them. So it's always nice to look at a pretty simulation. So we can look at what's called this period of cosmic dawn, which is, it's like the dawn of the universe, because these stars are really the first sources of light in the universe. So before that, it was just gas everywhere. There wasn't really any kind of radiation. And so you see, once these stars start to appear, this is a simulation of star formation, and you can see it's, a couple 100 million years after the Big Bang. As these stars start to appear, there's a zoom in here on something that's going to become a galaxy eventually. There are little pinpoints of light that are forming all along these stretches of gas and dark matter in the universe. And so this, you can see that it's a pretty simple process. It doesn't look as complicated as those molecular clouds that we saw before. And that's also because these stars form, basically, we think, one at a time or in groups of just a few, because they're so massive and so, so powerful. So we can return to our timeline in a slightly different format, and now think about, where do these stars fall in the evolution of the universe? And so over here we have the Big Bang, and that was the kind of stretched out part that we were talking about before. Then we have this period which is called the cosmic dark ages, because from the Big Bang we see that cosmic microwave background, which is the furthest light that we can see from the universe. Then we have a period of time where there is no structure. There are no stars, there are no galaxies, there's nothing in the universe. It's just hydrogen everywhere. And so for that period of time, the universe is effectively dark. Then 200 to 400 million years after the Big Bang, the first stars form. And once they form, we have cosmic dawn. There's light in the universe. And as they bring light to the universe, they start this process called reionization. So this means, you saw before that those hydrogen atoms get ionized, the electrons get knocked off of the hydrogen. And that happens from these stars emitting photons. And as this happens, the stars create little bubbles of ionization around them, of ionized hydrogen around them. And those bubbles will start to grow over time. And as you get galaxies, those galaxies will also emit photons because they have lots and lots of stars in them. And eventually the universe becomes ionized. It becomes mostly full of hydrogen that has no electron. And so that's actually what we see in the universe today. And so then you see that we evolve and we get all of this other interesting physics, which you'll hear about from other people. But that's for the later 10 billion years of the universe. In the first billion years, we have just the first stars and the first galaxies. And so the physics, we think, is relatively simple to describe. And so I guess another interesting thing that happens with these stars is that when they die, some of them may go into supernovae. So they may explode like those massive stars that we saw before, because they are massive, just like those stars that seeded those supernovae in the simulation and the artist conception that I showed you. And when they do that, they will basically expel all of these. So in the core of the star, I guess, one thing I forgot to mention is that as they fuse hydrogen into helium, then eventually the star becomes massive enough that it can start to fuse helium into heavier elements. And so that's where the heavier elements that we see in the universe, like carbon and oxygen and things like that, come from. They come from the cores of stars. And then the way that those elements get to the rest of us, or get to the rest of the universe, is by the stars expelling them in their supernovae. So you get, once these stars end their lives, they expel a whole bunch of metals into the universe, and that results in the universe starting to have metals. You start to have more molecules, and then you basically can no longer form stars like the first ones. So that sends us into the next generation of star formation. And so another thing that I think is interesting to point out is that these first stars may have been the seeds for the first black holes. And so what that means, and I'm not going to talk about this too much, is just that some of these stars may not have ended their lives in a huge explosion like a supernova, and they may actually have just, collapsed in on themselves. They got too big and collapsed down to become a black hole. And those black holes will then grow over time, and they may have, been the seeds in that sense, or the parents of the black holes that we see today. Like here is Sagittarius A star, is the black hole at the center of our galaxy. And here is M87 star, it's a black hole in a nearby galaxy. So I'm not going to talk about this too much, but that's just another interesting point that we can talk about more if anybody's interested. So then the question is, how do we observe the first stars? And this is a difficult question. I said that we haven't observed them, so you already know that this is going to be challenging. But yeah, so let's talk about that a little bit. So part of the challenge with observing the first stars is just that they're really far away. So this is, the astronomer that. So this is akin to the problem of, just zooming out from something really, really far. The Earth is really big and reflects a lot of light from the sun, but as we move further and further away from the Earth, it becomes harder and harder to see. It becomes just a point of light, just like any other star or object that we might see in the sky. And as we move really, really far away, you can see we get this, this is the famous image from the Voyager satellite, or that when it was leaving the solar system, it took this picture of Earth, and we see it as a pale blue dot. And so that's one challenge. The stars are just really far away. They're in the very, very early universe, so they're really hard to see. Another challenge is that there's lots and lots of gas between us and the stars. So it's like looking for points of light, but you're looking through a huge amount of fog. And so this is like, driving down the street and you see cars and it's a really foggy day. All you can really see are the headlights. And even those are kind of obscured by the fog that's in between you and those lights. But except in this case, these lights are millions, trillions of miles away, and the fog is almost opaque to the light, so we can't actually see anything that comes through it. So then what we have to do is become a little bit creative. And so this is where astronomers have thought about potentially observing these stars indirectly. So the idea here is just like if you were walking along and you were on this side of this, set of houses, you can't really see anything on the other side of this first one. You can't see through the house. And suppose there was a fire, you may not be able to actually see that fire, but you can study the fire, or you can know that there's a fire happening because you see the smoke. You see an indirect signature of the fire that's, burning down this house. And actually closer to what another thing that you might be able to do to see that this fire is happening, and closer to what we do for these stars, is that you might be able to smell that the fire is happening. So you wouldn't actually even see the smoke, you smell the smoke. And so you have to become very creative to study those stars and to think about their indirect signatures. So, so for a quick recap on how they affect their environments, like I said before, you have hydrogen around these stars in the early universe. Then a star appears. The star emits a photon that interacts with the hydrogen, and then it breaks it apart. So you get this ionized hydrogen, which is just a proton here and an electron. Then the star does this all around itself, and it creates a little bubble, and it basically makes the hydrogen gas all through the universe look like Swiss cheese. It creates these little bubbles of gas everywhere. And so we can actually study that structure. We can study the Swiss cheese structure of hydrogen in the universe by going out and looking for what does the neutral hydrogen look like all the way back in the early universe? Of course, this is also challenging because neutral hydrogen emits in radio wavelengths, so we can't study it with traditional telescopes, thus by looking out with like the Hubble Space Telescope or the James Webb Space Telescope or something like that. We instead need to look in different wavelengths of the electromagnetic spectrum. So here's a quick recap of multi-wavelength astronomy. So here's an analogy to looking in multiple wavelengths and what that can tell you here on Earth. You could go to the doctor and say that your arm was hurting, but just looking at your arm in visible light, you may not be able to see what's going on. But if you looked at your arm in X-ray light, you would find out that perhaps you had, really severely broken your arm here, and you needed to get like a cast and a splint and stuff. And so that's how looking in different wavelengths helps you here on Earth. And then in astronomy, we can think about what different structures multiple wavelengths allow us to study. So here's the galaxy Centaurus A in visible light. So this is how the galaxy might look to us if we were just walking along and we saw it. But if we looked at different wavelengths, like we looked at X-ray light, which is here, infrared light, and radio light, we actually see this much more complex structure to the galaxy. So we see that same kind of structure that we saw before, but then we also see these plumes that are coming from the black hole at the center of the galaxy, ejecting dust and gas. So I'm going to skip this. This is just another video that shows the same thing. But the idea is that you can learn a lot about an astronomical source by looking at different wavelengths. So here's just another way that you can see. So I showed you that picture of the black hole. This is what that black hole looks like all across the electromagnetic spectrum. So from the really long waves, like radio waves, you see the jet from the black hole. That's what all of these are. And then if you go to the super high energy or short wavelength end of the spectrum, you can see things like, these gamma rays and X-rays that are coming from the black hole. So this, I'm not going to talk about this too much, but this is just another example of how you can learn things with multi-wavelength astronomy. However, it's also tough to do this from the Earth's surface because the Earth's atmosphere blocks a lot of light. It blocks these high energy light like gamma rays, X-rays, and UV rays, which would be harmful to us. We see visible light, but then radio waves might actually be observable from the Earth's surface, some of them. So, so finally, I know I'm low on time, but I just want to give one more quick poll so we can understand what's going on. So I want you to tell me, what do you think? Which telescope captured this image on the left?
I wouldn't think that's too difficult because in iTelescope, there are quite a few people who've done this one.
Well, I hope so.
Oh, yes, it's a very favorite target. It is. Yeah, I think this is probably going to be the easiest one.
So we have three choices here. We have the Very Large Telescope, which is 8.2 meters. We have the Level Telescope, which is 76 meters, so that's pretty big. And we have the Skywatcher Telescope, which is 100 millimeters. So see what people think.
Okay, we'll end it and we'll share the results.
See the Skywatcher Telescope. Interesting. This is taken with the Very Large Telescope, actually. So it's this is a pretty high resolution image, but yeah, I mean, I think it looks kind of like what this would look like if you took it with the Skywatcher Telescope. Well, we keep going. Whoops. Okay, which telescope captured this image? What do you think?
Okay, wait a second. Let me just try and launch this one. Wait a minute. Sorry, I must just get to the right pole here because stop sharing. Let me just get this one. Okay, launch this one. Okay, there we go. Oh, that one. That's a good one. Although I must say the M33, if we put a half meter on there, we'll get quite close, actually. I mean, it sounds crazy, but we'll get a very good picture. That's also why I think you saw so many on the 100 millimeter, because people are actually quite spoiled. If you got very good skies like in Chile or so, and you got a half a meter telescope, you can do very well, actually,
Yeah. Yeah, I think you could observe it very well. I think this is just to illustrate a different point. Eh?
Yes. Okay, we're getting here a lot in there. Yeah, I think this is probably a bit easier. Could be the Sky Watcher with a lens cap on it. That would happen to me. That's what happens.
Yeah.
Okay, I'll share this one.
Okay, cool. Yeah, so we picked up on that. Yeah, this is taken with the Lovell telescope. And then finally, this is what you would take if you were looking with the Skywatcher telescope. So you see, you get a pretty good image with the Skywatcher and the VLT, with a very large telescope. But we got a kind of bad image with the Lovell telescope, and we might wonder why. And that's because the thing that I did not tell you was that telescope is observing in the radio, whereas the other ones are observing in the optical. And so the basic idea here is just that the angular resolution of the telescope, or the minimum separation that you're able to resolve on the sky, is related to both the wavelength of the light that you're observing and the size of the telescope. So it's not just that a bigger telescope will be better. You also need to think about what kind of light you're observing. So yeah, and I guess if anybody's never heard of angular resolution before, you can basically think of, if you had 2 points of light and you brought them really close together, this is the minimum distance that you could bring them together before they would look like 1 point of light on the sky. So this Lovell telescope is observing in the radio, where the wavelengths are, thousands of times longer than they would be in the optical. So you basically increase this size while not increasing this D very much, and you end up with an image that isn't super high resolution. So the way that we get around that with our radio telescopes, if we're trying to observe very detailed structure, is with interferometry. So that basically means, if you think about it with 2 radio telescopes, you put these 2 telescopes far away and you observe the same source of light in the sky, and then you account for the difference in time that it takes the light to go to the 2 telescopes, and you can, from that, create a telescope that's effectively as big as the separation between the 2. So if you put these 2 dishes 100 miles apart, then you would have a telescope that was 100 miles big, and you start to get much better resolution with your interferometer. So that's what you can see here. As they move apart, you get better resolution of this source. Now you can, here at the bottom, you can imagine distributing a whole bunch of these, not just 2, and then these things are on Earth. So if you take a bunch of images of the same thing, as the Earth rotates, their position will actually change. And so you can see that's what's being shown in the animation here, where the space between these individual nodes or antennas gets filled in, and you can get a really crisp image with an interferometer like that. And you get this huge, it's effectively like a telescope the size of the Earth, which is pretty impressive. So this is just another illustration of that with the National Radio Astronomy Observatory here in the US. And you can see that if you build out this grid of antennas, the image gets better and better. And then as you include the Earth's rotation, then you get a really crisp image of a couple sources. So the result of that is that you can go from this image to this image. So this is how the light from this galaxy would look at wavelengths of 21 centimeters rather than, a couple hundred nanometers, using a radio array, like the very large array. So this is the idea of how we study the first stars, is by using radio interferometers. And so here are some examples. Here's a collection of dishes, the square kilometer array. This is not actually fully built yet. This is a planned project. So this is an artist's rendering, but this is going to be built largely in the next 10 years. Parts of it have been built now, but so this is going to be one of the things that'll help us study the early universe. But radio telescopes also come in many shapes and sizes and forms. Here's an example of one. This is the Edges radio telescope, and it's really just a metal table that's out in Australia. And it's just a single antenna, actually, because it's measuring the signal from the whole sky. So it doesn't need to be super high resolution. It just needs to be super sensitive. And so you have this radio shield around the antenna. And I think this is actually a very creative idea for a telescope. It just looks like a table that somebody left out in the desert. Another, interesting looking radio telescope is the Hera array. So this is another telescope that's intended, this is in South Africa. It's intended to study the early universe. And this is also a very simple telescope. It's just a couple planks of wood and some wire connecting them. And it's this huge interferometer that's going to measure the hydrogen gas in the early universe. And then finally, another group that I'm part of is trying to work on putting a radio telescope on the moon. So this is actually very interesting because this allows you to look into the really early universe, because it eliminates a lot of the noise that we get in the radio range from, people here on Earth. So I can talk more about any of those, but I just wanted to mention a couple different radio telescopes and show how they can look very different based on what you're trying to do. So I think that takes us to the end, but I'm happy to answer questions if people have any.